integral calculus, and in this video we are going to consider a number of topics that are involved when you're dealing with integral calculus. One of the topics is the basics of integration. What is integration all about? Then we're going to look at how to integrate. Integration using trigonometric substitution will be the third video. Then the fourth one will be integration using substitution method, followed by integration by parts, integration of partial fractions, integration of indices, numerical integration, how to apply integration in daily lives or applications of integration. Then we are going to compare the similarities and differences between differentiation and integration. Then we consider double integral, triple integral, and then we have other topics, 3 of them. We have the Taylor series, how to test a series for convergence, and partial differentiation. So those are the 13 main areas of integration that we are going to look at in this video. And please remember to subscribe to Teach Quant so that you can always get more update videos in the future. Thank you.
So we want to look at basic integration, and we start by looking at a simple example of indefinite integral. What do we mean when we say this is an indefinite integral? It's an indefinite integral because we are not given the limits of integration that we're going to use. And this is a basic example that we can have. So we can write this equation as this, a half outside because a half is a constant. And I'm going to integrate x squared with respect to dx. And that basically gives us a half, then times x. What do we do to the power? We increase the power by 1, and then we divide with a new power, which is 2 plus 1, and then we add a constant. Therefore, it is a half times x cubed over 3 plus c, which I can also write as x cubed over 6 plus c. So that is the integral. Remember, it's an indefinite integral, so I have to add the constant of integration. So the c is what we call constant of integration. So that is our c, the constant of integration, that you should add whenever we are dealing with an indefinite integral. Now, let's move on and look at another example, but this time we look at what I would call a definite integral. So number 2, I'll define it as a definite integral. And then you'll see the difference between the two. So when you're dealing with an indefinite integral, you have to add the constant of integration. So for example, if I was to integrate this gives me x, keeping in mind what we did to the power. In the previous case, we said 2 plus 1. So now we say 3 plus 1, which is 4. We divide by 4. I don't need to put in the constant of integration when I'm dealing with definite integrals. And it's a definite integral because I have the limits of integration from 1 to 3. And how do I deal with it? It is 3 to the power 4 over 4 minus 1 to the power 4 over 4. So that's what we have. And you can have the outside. Once you're done, you bring it back. Or I just divide with it. 3 to the power 4 basically is not a small number, it's 81. So it is 81 minus 1 divided by 4, which is 80 divided by 4, which is 20. So for the definite integral, you do not need to put the constant of integration. And if you're very careful with what you're doing, you shouldn't find any challenges in that. And that's another example of how to deal with a definite integral and indefinite integral. Again, if you like my videos, you are welcome to subscribe, or also press the like button so that you can be able to get more updates as we move along, as I continue updating them every time. To look at a number of integration problems, and the first example we want to look at is how to integrate the integral of 1 to 3 to all over the square root of x dx. And this, I can also comfortably write it as this. I've put 2 outside because I know that 2 is a constant. And the integral rule says, what do I do to the power? I increase the power by 1. So negative a half plus 1 is a half. So it is x raised to power half. And then I divide by a half. And then I put the limits of integration. And you've seen that I've not put in the constants of integration because I did not see the need to do so. And this automatically becomes a half. 2 divided by a half. I'll leave it as it is now. It is 3 to power a half minus 1 to power a half. 2 divided by a half is the same as 2 divided a half, which is 2 times 2, and this is 4. So the answer will be 4. Then the square root of 3 minus 1, which I'll comfortably leave out for you to get a calculator and be able to key in those values to see what you get from that computation. After all, even if you are to leave it that way, I don't think it will affect anything so long as the answer is okay. The second integral we want to look at is 4x cubed dx, which I can write as 4, the integral of x cubed dx, which will basically be 4 x to the power 4 over 4 plus c, which is x raised to the power 4 plus c, which is a constant. Because this is an indefinite integral, we have to put the constant of integration. So that's another example that we have looked at. The third one is a simple one also. We want to integrate from negative 1 to 11 x raised to power 1 to power 1 over 11 dx. And I want to reduce this by letting u is equals to x plus 1. And then I have du dx as equals to 1. So if what we have here is that dx is equals to du. So I'll be having the integral of 1, negative 1 to 11, u raised to power 1 over 11 du. What do you do to the powers? You increase the power of, by 1, so it will be 1 over 11 plus 1 divided by 12 over 11. And that's what we get from that. And so, because our integral was originally in terms of x, so I'll have x plus 1 raised to power 12 over 11. Here I have divide by. So if I divide here, it's like I'm taking 1 all over 12 divided by 11. And then I have negative 1 to 11. And so this will be affected. This will be 11 over 12. This is 12 raised to power 12 over 11 minus negative 1 plus 1 is 0 raised to power 12 over 11. So the answer will be 11 over 12 times 12 raised to power 12 over 11. Is the integral of 12x squared plus 4 divided by 4x cubed plus 4x dx. So what we do is we let u be equals to 4x cubed plus 4x. So du dx, du divided by dx is 12x squared plus 4. Then I have dx is equals to du divided by 12x squared plus 4. So now I'm going to substitute u and dx into the original equation that I have, and I see how my problem simplifies. So I have 12x squared plus 4 over u times du over 12x squared plus 4. And that simplifies to du over u, which I know it is the ln of u plus a constant. I'll put a constant when the limits, there are no limits of integration, or it's an indefinite integral, and that gives me the ln of 12x squared plus 4 and then plus c. In other terms, can put it in a simpler manner to make it look a little bit more appealing to each one of us. So that's what we have. In the final solution that we get in that equation number 4 that we have solved. And this is the integral of x raised to power 7 plus 3x raised to power 4 plus 2x squared dx. Remember, because you're integrating, you just increase the power by 1, you divide with the new power. You increase the power by 1 and you divide by new power. You increase the power by 1 and you divide by the new power. That's basically what you do with the change of color that I've done. So this is x raised to power 8 over 8 plus 3 over 5 x to power 5 plus 2 over 3 x to power 3. And because it is an indefinite integral, you introduce a constant into the integration that you have. So that's what you get in that integral that you have. And then we have pi sin or sine of x over 2 dx. So what I'll do is I let u be equals to x over 2, then du over dx. Du over dx is equals to a half. Dx is equals to du. So then I'm going to change my equation slightly to make it easier for me to integrate 0 to 5 pi. Then it will be sine of u times 2 du, which will be minus 2 cos u. But before I can substitute my limits of integration, I have to rewrite back in terms of x. Otherwise, I have to do a full transformation of the equation. It will be minus 2 cos of x, not pi, cos of x over 2. And it's 0 to 5 pi. And that will take me to another level. And that gives me negative 2 cos of 5 pi over 2 minus cos of 0. And whatever solution you get, And I think this will give us 2 as the answer because, yes, I think cos of 5 pi will be 0 because this is an odd one. And it's another day, and we want to look at integration using trigonometric substitution method. And we have an integral there that well fits the method that we want to apply. So we want to look at how to go about solving this integral using the substitution, trigonometric substitution. And I'm going to introduce in the variables that help me deal with this part. The first knowledge before even we go to introducing this is I want us to keep in mind this identity that sine squared x plus cos squared x is equals to 1. Or in other terms, if we want to put it in a more better way, cos squared x is equals 1 minus sine squared x. So in a nutshell, because this is a square root, I want inside this square root to be left with 1 minus sine squared x. Because I know that 1 minus sine squared x will give me cos squared x. So I need to deal with 3 and 5 in such a way that they will not affect my solution. Or I could even factor them out, literally. So what I could do is I could think of a way of rewriting the same equation such that I'll take out the 3 and 5. And one way of doing that is by being a little bit clever in the way I select my x. So my x will be the square root of 3 all over the square root of 5 sine theta. I cannot say sine x because I'm saying let x be equals to that. So you see here what happens? It will be, if I square this, x squared will be equals 3 over 5 sine squared theta. And you can see what will happen. The 5 and the 5 will cancel. Then the 3 and 3 I will be able to factor out. But I'll come back to that in a moment. So I let x be equals to, then this is where the trick is. And that is where the challenge could be, the selection of this part. I have to be a bit keen with it so that I'll be able to solve out my equation easily. So a number of things I know about this. I need to change from the x to d theta. So now I find out what is dx d theta. It will still be square root of 3 over square root of 5. The d theta definitely changes. What do I get? I'll get cos theta. So now I have my x squared, and also I have my dx. But now I need to take the dx, the subject of the formula. So dx will be equals to the root of 3, the root of 5, cos theta, d theta. So I have the two parts. I have my dx and I have my x. So those are the two I want to take now into the equation. So let's get back to our original equation and see what that means when we are doing the integral. So our integral is dx over 3 minus 5x squared. Let's put them back. I'll start with dx. It's root 3 over root 5 cos theta d theta. Now let's come down here. It will be the square root of 3 minus 5. You remember x squared, it was 3 over 5 cos, sorry, not cos, but sine squared. Now you understand why I took the square root over 3 over square root of 5 as then sine theta as my x, so that when I square, it becomes 3 over 5. Now you can see the 5 and the 5 cancels. These 3 and that 3 are common to each other. So I'll be able to take it out. I'll be left with 1 minus sine squared theta. Let's take the next step slowly. That will be together in that. So it will be square root over 3 of square root of 5, the integral of cos theta. Here, it is a square root of 3, 1 minus sine squared theta. Obviously, we are integrating with the theta. And you know, 1 minus sine squared theta is cos squared theta. And it is a square root. So we have the square root of 3, and then the square root of 1 minus sine squared theta. So 1 minus sine squared theta is cos squared theta. So that's what I want us to remember. 1 minus sine squared theta is equals to cos squared theta. And so the square root of cos squared theta is equals to cos theta. So there, this is now what happens based on that knowledge there. So this becomes square root of 3, square root of 5, cos theta, d theta, all over root 3, cos theta there. And therefore the cos theta and the cos theta will cancel out. I'm sure this will be root 3 over root 5 divide root 3. And when you introduce multiplication, then automatically that will cancel out. So that becomes clear for us now when we do that math. And therefore, this gives me 1 over square root of 5 integral of d theta, which is 1 over square root of 5 theta plus c. That is our solution, but I would not leave the answer to that point. Why? Remember, our original equation was in terms of x. So I need to write back, introduce my x, so that I can write the answer as x. We had said at the beginning that x is equals to root 3 over root 5 sine theta. Therefore, sine theta is 5 over 3 to power a half times x, which is true. And so I want to make the subject of the formula. Theta will be the sine inverse of 5 over 3 square root of x. And then I can substitute that into the equation. And therefore, I can comfortably say that the solution for my equation is dx over 3 minus 5x squared should be equals to 1 over root 5 sine inverse of square root of 5 over 3x plus c. I hope you've been able to follow through the steps. You can review the video again. And again, if you like the videos that have been, kindly subscribe. And I want to thank you so much for your time. So, we want to look at the integral of the form. I have two forms here. The first form is where I'm dividing the derivative with its original function. And the second form is where I'm multiplying the derivative with its original form. So I have two forms that I want to look at, and I have the two examples. So I'll start with our first example, 2x plus 3 divided by x squared all over x squared plus 3x. So in the first form, I let you is equals to x squared plus 3x. Then I have du over dx is equals to 2x plus 3. And therefore, I make dx the subject of the formula. And that's what I get. And that's what I get from that. Now I go to the original equation, substitute in the values. And therefore, that's what I get. I get 2x plus 3. Instead of writing x squared plus 3x, I put u. And instead of dx, I put 2 du over 2x plus 3. And this will cancel out. And what I'll be left with is du over u. What is the integral of du over u? If we ask ourselves, and that gives me ln of u plus c. And therefore, what was my x? What was my u? It was x squared plus 3x, and then plus a constant. Remember, we always put a constant of integration whenever we are dealing with indefinite integrals. The second form of equation that I have is the integral of sine x times cos x dx. How do I approach this? The approach is almost similar, just slightly different, where I let u is equals to sine x. So then I get the first derivative. What is du dx of that? And we know that the first derivative of sine x is cos x. So du dx is equals cos x. If I make dx the subject of the formula, it will be du over cos x. Now, let me go back to the function and write it down. So I substitute back sine x. And I know what is the value of sine x. Instead of writing sine x, I know I'm going to write u. And then I'm going to put cos x. Instead of dx, I write du over cos x. And again, those two cancels. And I'll be left with an integral of u du. And what does that give me? And that goes up to u squared over 2 plus c. And I know what is u is sine. That's so I can write it as a half sine squared x, sine x squared plus c. And that definitely gives us the solution to the two integrals. So you can review that and you realize that it's very easy to integrate such types of equations of this form that you have looked at today. And thank you for watching this video, and I hope you've enjoyed. We want to consider integration by parts. And what we have there is a formula that we can use when we are dealing with integration by parts. And today we want to look at an example of integration by parts. And we want to look at the integral of ln of x dx. And to help us have a u and dv dx, then we introduce a number, which is 1, because we know that if we multiply 1 times ln of x, it's still ln of x. And then from there now, we can be able to obtain our u, which will be expressed as ln of x. And then I can get du dx according to the general formula that we have there. And the first derivative of ln of x is 1 over x. After getting u, we need to get v. And we have dv dx as 1. And therefore v is the integral of 1, which is x. So I can comfortably say that ln of x dx will be equals to, looking at the general formula, u times v, which is x, ln of x, minus the integral of v x times du dx. And clearly we can see here that the u, the x, and the x will cancel out. So here I'll be left with 1. And the integral of 1 dx will give us x. So then it means basically that the general solution becomes x ln of x minus the integral of 1 is x plus c. And note that if you are to differentiate x ln of x minus x plus c, you get ln of x. You can try to do that and see what you get. And I'm sure if you like my videos, you should just press the like button and also subscribe so that you can get the update to newer videos that will be coming up. Today, we want to look at integration of partial fractions. So it is integration of partial fractions or integration using the technique of partial fractions. We have an example, x plus 1 divided by x squared plus x minus 12. So the first step I want to take is I want to look at the denominator. And I want to factorize this, and this will give me x minus 3 and x plus 4. So x squared plus x minus 12 is the same as x minus 3 times x minus 4. And why is that important? Because I want to take my partial fractions and I want to take my integral and I want to break it down into partial fractions. So that's what I want to do. And that will make it easier for me. So I'm going to introduce two unknowns and I'm going to solve them so that I'll be able to break down my equation. So that's the first step. And then I want to multiply it through by this. I want to multiply it through by this. So it will be x plus 1 is equals to x plus 4 a plus x minus 3 b. So that's the first step. I multiply it through with x minus 3 and then I multiply with x plus 4. And then I'll open up the brackets. So I'll have x plus 1 is equals to ax plus bx plus 4a minus 3b. So what have I done? I have put like terms together. And so why is that important? Because I want to compare similar terms together. And that will make it easier for me. So you can see the components without the x, I put them together, and the components with the x term, I put them together. So I can comfortably say for the first equation, it is ax plus bx. And if I divide through by x, it implies that a plus b is equals to 1. And then in the second equation, 1 is equals to 4a minus 3b. So therefore, I have two equations. I have one here, and I have my second equation there. So I have those two equations that I'm going to use to be able to solve for a and b. And that will make it very easy for me to be able to solve, to get my two partial fractions. So when I put my two equations together, this is what I'll get. I'll get a plus b is equals to 1, and 4a minus 3b is equals to 1. I make them the same by multiplying through. In the first equation by 3, 3a plus 3b is equals to 3, and 4a minus 3b is equals to 1. Why did I multiply the first equation by 3? So that I make the parameter or the letter b to be equal in the first and the second equation. But when I sum them up, what happens? I'll get 7a is equals to 4. So comfortably, a is equals to 4 over 7. And b is equals to 1 minus a, which is 1 minus 4 over 7, which is 3 over 7. And now remember, how we wrote down our equation at the beginning. We said that x plus 1 over x minus 3, x plus 4 should be equals to 4 over 7, 1 over x minus 3, plus 3 over 7, 1 over x minus 4, or x plus 4. So already I've been able to break down my integral into two partial fractions, a and b. So instead of doing the integral of this, I'll do the integral of this, and then I'll just introduce the dx into each of them. And that's how I'll go about it, and that will make it easier. Or as we are familiar with how to do the integral of that, and therefore the integral of x plus 1, x squared plus x minus 12 dx will be equals to 4 over 7 ln of x minus 3 plus 3 over 7 ln of x plus 4 and then plus c. And that gives me the solution of that. Again, if you like my videos, kindly subscribe so that you continue to receive more updates of the videos as we move along and get newer videos every day. The integration of indices is what we want to look at. We have an example of 5 raised to power x plus 3 dx. Note that when we are integrating, the base should always be x. And in our case, the base is a number and the power is the x. So we want to interchange the equation in a way that we can make the base x. But this time now we are going to introduce u so that we'll be able to integrate it in an easier form. So if I let u be equals to x plus 3, I'm going to introduce the ln on both sides of the equation. And if I introduce this, then that makes it easier for me to write this comfortably as that. So ln of u is equals to x plus 3 ln of 5. Then from there, what do I do next? I want to substitute, because now I've introduced u in place of x. I want to introduce du in place of dx. So first of all, I'll differentiate this with respect to x. And you'll note that because u is not a variable similar to x, then I'll introduce what we call the implicit differentiation. So I'll get 1 of u du dx is equals to. Now, I'll use the product rule to differentiate these two parts here. If I differentiate x plus 3 with respect to x, I'll get 1 plus times ln of 5. Then plus, I keep x plus 3 constant. I differentiate ln of 5 with respect to x and I get 0 because ln of 5 is a number. If you go to your calculator and punch in ln of 5, it will give you a number. So automatically then, this on my right-hand side, I'll be left with ln of 5. If I make the dx the subject of the formula, then I'll be left with du all over u times ln of 5. That's what I'll get if I make dx the subject of the formula. At this point now, I want to take my u, which is 5 raised to power x plus 3, put it into the equation. So where there is 5, x plus 3, I'll replace it with u. And where there is dx, I replace it with du divided by u over ln of 5. So I'll go to my equation, which was 5 x plus 3 dx. And where there is 5, I'll put u. And where there is dx, I'll also put d. I put du over u times ln of 5. So I'll comfortably be left with the integral of du all over ln of 5. And that's what we have. And then ln of 5 is a number, as I've said before. So I'm going to take it exactly the way it should be. So it will be 1 over ln of 5. When I integrate the u, I'll be left with the u plus c. And we know what is u? U is 5 raised to power x plus 3, then divide by ln of 5, then plus c as a constant. So that is how we would have integrated, or that's how we approach these type of problems. I'm sure you love my videos. Then why have you not subscribed? Please go ahead and subscribe, and I'm sure we'll continue to get more videos as we move along, so that you can continue to see how to face these different types of integrations that we. For the numerical integration, we want to look at the trapezoidal and the Simpson rule. That are techniques for finding definite integrals numerically. And we're going to look at two methods, the ones we have mentioned. We have the trapezoidal. We have the trapezoidal rule formula that we want to put down, and that's the formula that you'll be looking at and using to do an integral fb of f of x dx. Should be approximated by h, a half y naught plus y1 all the way plus yn minus 1 plus a half yn. And that is a formula that we use for the trapezoidal. And the example tells us that want to find the integral from 1 to 3 e of x squared dx with n is equals to 6. So we want to use the trapezoidal rule, integrate that with n is equals to 6. So what is involved? The procedure is quite straightforward and simple. The first thing is we need to get h. H is normally given by b minus a divided by n. Our b is 3 minus 1 divided by n, which is 6, which is 2 over 6. And that gives us 1 over 3. So we have gotten h as that. The next step is now we go on and our first value is a, which is 1. And we give it an increment of h. So 1 is 3 over 3, that's 4 over 3, 5 over 3, 6 over 3 is 2, 7 over 3, 8 over 3, and 9 over 3 is 3. And that makes our b. And then we have our y. Y is equals to e x squared. So this is e raised to power 1, e raised to power 16 over 9, e raised to power 25 over 9, e raised to power 4, e raised to power 49 over 9, e raised to power 64 over 9, and this is e raised to power 9 because it is x squared. And this is also our x values, those values there, and therefore this becomes our y, y0, y1, y2, y3, y4, y5, and y6. So now we have got all the values. Now what is left is for us to solve the problem. So the integral of 1 to 3 e of x squared dx is h, which is that. Then y0 is that, y1, y2, y3, y4, y5, and then y6. And that's the computations that we have. If we put all that together, this will give us that, and relation for that problem is given by 1862.159 using the numerical integration. So the Simpson-Lou formula, if we are to integrate from a to b, f of x dx is h over 3 y0 plus 4 y1 plus y3, and then plus 2 y2 plus y4, and then plus yn. Just a similar example, and we want to find the integral of 1 to 3 e of x squared dx with n is equals to 6. We add that just as in the case of the trapezoidal rule. That's the first thing. But now there will be a few changes here and there because of the formula. So now we have our value of x. Our a is 1, then 4 over 3, 5 over 3, 2, 7 over 3, 8 over 3, 3. And then we have y is equals e x squared, e raised to power 1, e raised to power 16 over 9, e raised to power 25 over 9, e raised to power 4, e raised to power 49 over 9, e raised to 64 over 9, and e raised to power 9. And so this is y0, y1, y2, y3, y4, y5, and y6. Of ax squared dx is h over 3, which is 1 over 9. And then we have our values. The first value is e raised to power 1. Then the second one is 4. And what we have is e raised to power 16 over 9 plus e raised to power 4 plus e raised to power 64 over 9. And then plus 2 e raised to power 25 over 9 plus e raised to power 49 over 9 plus e raised to power 9. And therefore, if you do all those computations, it will give you 1 over 9. The first value is e raised to power 1, which is 2.718. And then the second part, which is 4 times those 4 series, will give you 5,144.092. And the third one is 2 times those 2 parts, which will give you plus 495.104. And then the last part, e raised to power 9, is 8,103.084. Is 13,744.998. So that's what we get, 0.22. And that is the numerical integration of that exponential using. I want to look at application of integration. A stone is thrown upwards from the top of a tower 40 meters high. Its velocity in an upwards dilation t seconds later is given by 50 minus 40 meters per second. Find the height of the stone above the ground 3 seconds later. So this is the ground. And so the stone is thrown and it's taking that. So this is the stone movement. This is the height here. This is 40 meters. And the stone is thrown and it moves in a certain trajectory. So this is the tower. And we are told to find how far the stone is 3 seconds later. What you have been given is the dh dt, and we are told it's 15 minus 40. To get h, which is the integral of 15 minus 40 dt, which is 15t minus 2t squared plus c. And what do we know? We know that at time 0, before the stone was thrown, h was 40. Because the person was already, or it was on the top of the tower. So using that set of information, then we want to substitute and find c. So just say 40 is equal to 0 minus 0 plus c. And that tells us to see that c is 40. So will be equals to 15t minus 2t squared plus 40. So we want now to find that t is equals to 3. h will be equals to 15 times 3 minus 2 times 9 plus 40, which is 45 minus 18 plus 40, which is 85 minus 18, and that gives us 67 meters because it's t squared, which is 9. So what do we conclude? Height of the stone 3 seconds later is 67 meters. Our second question is we want to find the producer surplus for Sx is equal to x squared plus 2x plus 4 when x is equals to 2. And so what do we know? At x is equals to 2, Sx or x of 2 will be equals to 2 squared plus 2.2 plus 4 is equals to 12. So producer surplus will be equals to 2 times 12 minus the integral from 0 to 2 of x squared plus 2 squared plus 2 times x plus 4 dx. That's what we have as a producer surplus. And this gives us 24 minus x cubed over 3 plus x squared plus 4x. We integrate from 0 to 2. And that gives us, this is equals to 24 minus 8 over 3 plus 4 plus 8. And that will give us a solution that is equals to 24 minus, this is 12, that is 644 over 3, which is 72 minus 44, which is 28 over 3. And rate of investment is given by IT is equal to 6 root 2 root T 6 root T. Calculate the capital growth between the 4th and 9th years. So that's the computation we want to do. And we want to look at the capital growth, which I represent by letter K, between a given time period. And that is the formula that I would want to use. So I'll integrate between 4 and 9. 6 t raised to power a half dt. And we increase the power, that gives me 3 over 2. I'll come and divide by 3 over 2 there. And then I'll put the limits of integration. So 6 over 3 over 2 is 6, divide 3 over 2. So it is 12, it will be 12 over 3. So it is 12 over 3. This is t, not 6. So it will be 9 raised to 3 over 2 minus 4 raised to power 3 over 2. So you get the square root and then you cube. So this will be 3 cubed minus 2 squared. So that gives me 4. 3 cubed is 27 and 2 cubed is 8. And that gives me 19. 19 times 4 is 38 times 2, which is 76. In the area formed by the curves y is equals to x squared minus 2x and y is equals to minus x plus 2. And if you plot them, that's the type of graph that you have at the end of the day. We find that y is equals to negative x plus 2 is on top of the other curve. And we are interested in the area that is formed in this zone. So that's the zone that is of interest because that's the area that has been formed. And now we are going to integrate x starting from negative 1 to positive 2 here. And then we take the upper curve minus the lower curve. And then everything we are going to do the dx. And that takes us to the next step, which is negative 1, 2. And that gives us 2 plus x minus x squared dx, which is basically 2x plus x squared over 2 minus x cubed over 3 between negative 1 and 2. And if we continue, that will give us 4 plus 2 minus 8 over 3. And then minus 2 plus a half plus a third. If I replace the limit of integration, and the final plus 2 minus 8 over 3 plus 2 minus a half minus a third. So that's what we have. So 4 plus 2 plus this is 8. 8 times 6 is 48 minus 16 minus 3 minus 2. That is 27 over 6, which is 9 over 2. We look at the relationship between differentiation and integration. And basically what happens is that if you are given a function here, and this function, what happens is when you differentiate, what happens is that you get the first derivative. If you have been given the first derivative and you integrate it, then you get the original function, and this is basically part of the key lesson that we learn in calculus. Given your f of x to be equals to x squared, therefore the first derivative of that will give us 2x. So for us to get the original function, f of x will then be equals to the integral of f prime of x dx. And that is the integral of 2x dx. Of integration, so we'll get 2 x squared over 2 plus c, which is x squared plus a constant. We want to look at the relationship. For number 2, we want to look at the relationship between tan x times sec x and sec x. So if we integrate tan x times sec x, we get sec x. And if we differentiate sec x, we get tan x sec x. So we can say then df dx will be equals to what? And we expect the answer to be equals to tan x sec x. Remember, your f of x, if I'm differentiating, I can write this as 1 over cos x, and this, I'm going to use the quotient law. To 1, my u prime is equals to 0, my v is equals to cos x, and my v prime is equals to negative sine x. And therefore, my df over dx is equals u prime times v minus sine x divided by cos of x squared using the quotient rule, which is sine x all over cos squared x. And that gives me tan x sec x. So the integral of tan x sec x dx will give me sec of x plus c. Just a constant of integration. So how do I do that? I'll take this and I'll write it exactly as sine x over cos x times 1 over cos x dx, and that will be the integral of sine x all over cos squared x dx. So I let u is equals to cos x, and I want to use a substitution method. Then I say du my dx is equals to negative sine x. And that means that my dx is equals to minus du all over sine x. And so that means then I can write the equation as sine x over u squared times negative du all over sine x. So what I'm sure about is that these two will cancel out, and that makes it easier for me. With that information, then what I have is a negative u raised to power minus 2 plus 1 divided minus 2 plus 1 du plus c. So, and that gives me 1 over u plus c. And we know what is 1 over u? 1 over u is 1 over cos x plus c, which will give me the sec x plus c. So I've shown that if I have a function f of x is equals to 2x all over x squared plus 1. So what happens to this variable? It is 2x over x squared plus 1. When I integrate, I get, and when I differentiate. So this is when you differentiate, and this is when you integrate. So that's what we want to show, that when I differentiate, I get that, and when I integrate, what do I get? So that we can link the relationship. So I'll start with the differentiation. F of x is ln of x squared plus 1. So the df over dx will be equals to. So how do we differentiate the ln? You take this, you differentiate it, and this gives you 2x. So I'll put 2x there, and then I'm going to divide with the original function. And that is the rule of differentiation. So I've seen that if I differentiate ln of x squared plus 1, I get 2x over x squared plus 1. What about if I do the integral part? So if I integrate 2x over x squared plus 1 dx, so I let u is equals to x squared plus 1, and then du dx is equals to 2x. And what does that give you? And that gives you tells you that my dx is du over 2x. So if I come back to my integral, I'll write it as 2x over u times du all over 2x. Again, we can easily see that that cancels. And if I integrate du over u, the integral, and this gives me ln of u plus c. And that is ln of u. My u is x squared plus 1 plus c. And that shows evaluate the double integral, and we want to evaluate 3x plus 4y. X and y lies between 0 and 1. So if I want to, I can either write it in this form, or I can also write it in this form. Fortunately that 3x, x and y, fortunately x and y are symmetrical. So that makes it easier for me. And I'll use the same rule of moving outward from the center. Meaning that if I start with dx, then I'll use the first limit of integration. So I want to integrate that with respect to x. It will be 3x squared over 2 plus 4xy. And I want to put the limits of integration as 0 of 1 dy. And that will give me 0 to 1. When x is 1, this becomes 3 over 2 plus 4y. Then I integrate with respect to y. So this becomes 3 over 2y plus 2y squared, 0 to 1, which is 3 over 2 plus 2, which is 2, 3 plus 4, and the answer is equals to 7 over 2. Integral of 0 to 2, 0 to 1, e of 2x minus y dy dx. Note that takes us to 0 to 2. We want to evaluate this with respect to y, so we differentiate the power and then we divide with it. So it is e raised to power 2x minus y, then minus 1, 0 to 1 dx. This gives me 0 to 2 minus e raised to power 2x minus 1 minus e raised to power 2x dx. Because I'm substituting whenever there is y, I replace with 1 and also with 0. And therefore, that gives me minus, I'm going to differentiate with respect to x, that is 2 raised to power 2x minus 1 over 2 minus e raised to power 2x over 2, and the limits of integration are 0 to 2. And what does that give us? This takes us to the point of negative e when x is 2, 4 minus 1 over 2 minus e raised to power 4 over 2. Then minus e raised to power 0 minus 1 over 2 minus e raised to power 0 over 2. So that's what we have, and therefore this will give us a half e raised to power 3 minus a half e raised to power 4 plus a half e raised to power minus 1 minus 1 over 2. And that's the equation that we have, and I can factor out 1 over 2 to make it look simpler. So it is a half. And this gives rise to e raised to power 4 minus e raised to power 3 minus 1 plus 1 over e, And that is the final solution to that equation. Triple integral. We want to evaluate the integral from 0 to 1, 0 to x, and 0 to xy of x dz dy dx. The best approach I take is this. I integrate this and then I take that limit. If I integrate y, I use that limit. And if I integrate x, I use that limit of integration. So z, so it will be 0 to 1 and then 0 to x. It will be xz, then 0 of xy, dy dx, and that will give me from 0 to 1 and then from 0 to x. If I substitute xy where there will be z, it will be x squared y dy dx. Remember that we are integrating with respect to z, so x is treated like it is a constant at that point. The next step now, I integrate with respect to y, so it will be equals 0 to 1, and it will be x squared y squared over 2, and then 0 to x dx, and that will give me 0 to 1. Where there is y, I substitute with x, so it will be x squared times x squared over 2 dx. And I know this is equals to, or that is equals to x to power 4 divided by 2. So the next point is to do the last integral, and this gives us equals to x to power 5 over 10, and the limit is 0 to 1, which is 1 over 10. Another example is the integral from 0 to 3, 0 to 2, and then 0 to 1, x plus y plus z dx dy dz. Again, I move outward. That means I start with the internal, both from the limits of integration and the integral with respect to, and that gives me 0 to 3, 0 to 2. I want to integrate with respect to x, which is x squared over 2 plus xy plus xz. And then I'm going to substitute the limits of integration from 0 to 1. So whenever there is x, I'll put 1, and therefore it is integral from 0 to 3, 0 to 2. When x is 1, it will be a half plus y plus z, then minus 0, so I'll ignore that. So if I integrate with respect to y, 0 to 3 is a half y plus y squared over 2 plus yz 0 to 2. And then I have dz. And therefore, again, that gives me 0 to 3. Where there is y, so it will be 1 plus 2 plus 2z dz, which is equals to 0 to 3, 3 plus 2z dz. And that takes us to our last point, which is equals to 3z plus z squared and 0 to 3, which will be 9 plus 9, and the answer will be equals to 18. How we can test for convergence, and I want to look at 3 different approaches. And so we can start with our example. We have a series here that we've been given, n from 1 to infinity, summation 3 over 3 raised to power n. And this we can write it as n from 1 to infinity, 1 over 3 raised to power n. And so the first method that we would want to attempt to use is we want to use what we call the ratio test. And I want to see how the ratio test works. One of the things we want to keep in mind is that we calculate the value of R, which is given by an plus 1 over an. And if R is less than 1, then the series converges. If R is greater than 1, it diverges. If R is equals to 1, we need to test. So you need to do further testing if the value is equals to 1. So based on that information, we want to single out our an. From the equation, then our an is equals to 1 over 3 n minus 1. And then it automatically means our an plus 1 will be 1 over 3 raised to n. And therefore now we can get the ratio, which is our R, and see how it goes. And we'll know if the series. We are testing for the convergence. So our R will be 1 over 3 raised to power n divided by 1 over 3 raised to power n minus 1, which is 1 over 3 raised to power n times 3 raised to power n minus 1. And that, if we can remember how to go about this, maybe I could explain it further. This will be equals to 1 over 3n times 3 raised to power n divided by 3. And that tells me that my R is that, which is less than 1. So the series converges by the ratio test. So the ratio test helps us to show that the series converges. So that's the first thing that we have seen. The second thing is we want to look at our second equation that we have. And our second equation that we have is given by summation n is equals to 1 to infinity of 2n raised to power 3n. And we want to use another test called the root test. And how does it work? Basically, the idea is the same. R will be equals to the nth root of an. And if R is less than 1, then the test converges. If R is greater than 1, it diverges again, just like in the previous case. And if R is equals to 1, we need to do further testing. But today we are just looking at simple examples on how to test for convergence. So based on that, let's do the tests. So R will be equals to the nth root of 2 over 3 raised to power n, and the nth root, which implies that R is equals to 2 over 3, which is less than 1. So the series converges by the root test. So that's the other thing that we found. So now with the second method, the root test, the series converges. We can look at another method, the third method. And we want to look at an example of an integral. For example, summation from 1 to infinity of n1 squared. And we want to use the integral test. What are we doing? We are testing for the convergence. And therefore, what I'll basically do, I'll integrate from 1 to infinity of 1 over x squared dx. And this is the same as negative 1 over x 1 to infinity, which is equals to negative 1 over infinity plus 1, which is 1. And what does that tell us? Because we have got a definite value from our integral, so the series converges by the integral test. So these are some of the examples that we have on how you can use the integral test. There are other ways of looking at it. We can look at even alternating series. We can look at the last example, number 4. And I want to see if it is alternating. How would we approach it? For example, negative 1 raised to power n all over n squared. We have seen 1 over n squared converges. What about this? Remember, this would look something like this. Then plus 1 over 2 squared minus 1 over 3 squared plus 1 over 4 squared, and the list goes on. Now this is what we refer to as an alternating series. We refer to this as an alternating series. So we use an alternating series test. And how does the alternating series test work? Alternating series test is also very practical. It converges if the absolute value of an plus 1 all over the absolute value of an is less than or equals to 1. And then definitely if it is greater than 1, then it diverges. So we have to get the absolute value. And so if you get the absolute value, we'll definitely be left with a very simple equation. So my R will be equals, the absolute value will be n plus 1 squared all over n squared. Because the other one is a negative value. And this gives me an equation of the form n squared plus 2n plus 1 all over n squared. So I can get limit as n tends to infinity of 1 plus 2 over n plus 1 over n squared, and this will tend towards 1. So thus converges. So the series converges. That should have been a little bit better, because the value of R. Why have I said that? Because now I see R is equals to 1, and this shows that series converges. Because we have said if it's less than or equals to 1, then it is going to converge using the method. We call it by alternating series test that we have applied. So those are some of the approaches that we could take when we are doing some of these tests for convergence. We want to consider the Taylor series, and we want to look at an example. So the Taylor series generated by f at x is equals to a is given by f of a plus the first derivative of fa times x minus a plus the second derivative of fa times x minus a squared over 2 factorial, and so on. So we want to consider an example, and the example we want is that we want to find the first 5 terms of the Taylor series for which variable. So we are going to look at 2. The first one is f of x is equals to ex at a is equals to 0. So we want to find the first 5 terms, and so that's where we start off. So the first one is we start with f of a. F of x is equals to ax, and therefore f of a, and remember your a is 0, is equals to a of naught is equals to 1. Then we first get the first derivative of ex, which is also ex, and then we put the f prime of naught, which is also 1. We know that is the same case for all of them because the derivative of e raised to power x always remains. So the second derivative of 0 should be equals to the third derivative of 0 is equals to the fourth derivative at 0, and all of them are 1. And therefore, since all of them are 1, what I'll need to do is now I can write the Taylor series, my first term. The first term is f of naught, which is 1. And the second one is f prime, which is 1. Then times x minus 0, which is x minus 0 is x. So in the second case, it will be 1 times x minus 0 squared over 2 factorial. So those are 3 terms. Then the fourth one will be x cubed over that. And the fifth one will be x to the power 4 over 4 factorial. So those are the terms that we have. And that basically takes me to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial. And I'm sure from there you can even form a pattern of what is happening. And I could even go a step further since now I've seen there's a certain pattern that is being formed, and I can definitely write a factorial there. So n from 0 to infinity. So I can comfortably write my ax as that. I'm allowed to write. Now what I've created is what I would now call a power series. From the Taylor series, now I'm already something new called a power series. Now this was an example when a was equals to naught. What would have happened if I had a case where the value of a was a value like 2? Nothing much would have changed. I would have just taken my first term and I've gotten e raised to power 2. Then I get the first derivative of this to be equals to ex, and therefore f derivative of 2, because my a, here I should have put a as 2, would have given me e raised to power 2. So basically, the second derivative at 2 will be equals to the third derivative at 2 will be equals to the fourth derivative at 2, and this will give me e raised to power 2. But then my equation would have been slightly different. My Taylor series would have been different because now I'm testing it at a is equals to 2. And therefore my ex at a is equals to 2 would have been f of a, then plus f prime times x minus a plus e2 x minus a squared over 2 factorial plus e2 x minus 2, which is a is 2, cubed over 3 factorial, then plus e2 x minus a is 2 raised to power 4 over 4 factorial. And those are my first 5 terms again. And I can factorize, or I can simplify this. This should not be a. This should be, yes, it's a, but I know the value of a. My a is 2. I can write this as e raised to power 2. Then I say summation n from 0 to infinity x minus 2 raised to power n all over n factorial. So again, you can see I've also another power series with a constant here because e raised to power 2 is a known value. So that is the Taylor series when a is equals to 0 and then a is equals to 2 for the exponential e raised to power x. What about if we pick in another slightly different example? Not very different, so we want to get f of x is the ln of 1 plus x at a is equals to 0. So the first one is f of naught, and we know that will be ln of 1, and ln of 1 is naught. And then we differentiate the function ln of 1 plus x. So how do we differentiate the natural logarithm? We differentiate 1 plus x, which is 1, we divide with 1 plus x. And then f prime of 0 will be 1 over 1, which is 1. The second derivative, f double prime of x, this is the same as 1 plus x raised to power negative 1. So what do? You take the negative down, then you increase the power by 1. And then the second derivative at 0 will be negative 1 over 1 squared, which is negative 1. And so that's what we have. And the equation, that's the second derivative of that. So far we have 2 terms. We need the first 5 terms. We go to the third derivative of x. We take it up, it will be negative 1 times negative 2. Then this becomes 1 plus x raised to power 3. Maybe I could use a star instead of the multiplication, so that we don't get mixed up. So it is like times, yes, it's times basically. So f3 at 0 is 2 over 1, which is positive 2 that we get there for the third. So now we have 3 terms. We need the first 5 terms. Remember the original first term was 0, so we need to differentiate again 2 more times. And that takes us to the fourth derivative with respect to x, which is 2 times negative 3 over 1 plus x raised to power 4. So f fourth derivative will be negative 6 over 1 is equals to negative 6. And then finally the fifth term that we have, f5 of x is negative 6 times negative 4 is 24 over 1 plus x raised to power 5. And then f of 5 at 0 is equals to 24. So now with all those values we've got, we can write down our Taylor series at x at a is equals to 1. So f of a is 0, so I'll leave it out. So it would have been 0 plus f prime of 0 is 1, then x minus 0, over 1 factorial if you wish. The second derivative was a negative minus x minus 0 squared over 2 factorial. So I'm not going to subtract with 0 again because x minus 0 is still x. The next term after negative 1, we had positive 2. Then we have 2x cubed over 3 factorial. Then after 2, we had negative 6, x4 over 4 factorial. Then we had 24, x5 over 5 factorial. So those are our 5 terms that we have. And we want to simplify. It's always very important for us to learn to simplify our mathematics. Therefore, we have ln of 1 plus x is equals to x minus x squared over 2 plus. Now, what is 2 divided by 3 factorial? Remember, 3 factorial is 3 times 2 times 1. So one of them divides, so it will be x cubed over 3. Then 4 factorial is 24. 6 and 24, you'll be left with 4 minus 4 over 4. And then remember, 5 factorial is 120. 24 and 120, you'll be left with 5, and the list goes on. So that is what you get from that. And again, you could write it down using the form of our power series, but this is very good to that point. I wouldn't do much with it again. But if you wish, then we could maybe write it from n from 1 to infinity, negative 1 raised to power certain power x over n. So when it is 1, it is 1. So this is n. When it is 3, it's 3. So when 1 is 1, so it is 1 plus 1. So that 1 plus 1 becomes 2. And a positive power there, even number, negative 1 to an even number will be positive. When n is 2, this will be odd, and then it becomes negative. So whenever n is even, n plus 1 will be odd, and that will be okay, and it will give us what we need. So this is again another power series, and that is how you normally get your Taylor series at a is equals to 0 or a is equals to 2, like the previous example that you have looked at. We want to look at an example of partial differentiation. Actually, we want to look at 2 examples, and we'll start with this, f of xy, meaning that the function f has 2 variables, x and y, which is given by equation x squared y plus x times y plus y. And so we want to look at the partial differentiation of x, f of x, or which we can write as df over dx. And so we are going to treat y as a constant throughout, and we'll be dealing with x. So in the same case, in the first case, I'll have 2xy plus y, and then plus 0, which I don't need to write down because the last variable does not contain an x. So I'm only interested with x. And I can also get the second derivative, which you can write it that way, or we can write it in this form. Again, 2 and y are constant, so I'll be left with 2y, and that gives me the final solution for that equation. What about f of y, or the partial derivative of f with respect to y? Let's go back to the original equation. It's x squared y, so it will be x squared, because if I differentiate y, I'll be left with 1. And then plus xy, if I differentiate y, I'll be left with x. And if I differentiate y, I'll be left with 1, because the derivative of y is 1. So what you are doing is you are treating one of them like a constant, but it is not. And then the second derivative that we have which is d squared f over dy squared, will definitely be equals to 0. Why? Because in C, none of the variables, it's x squared plus x plus 1. There's no y. So x is being treated as a constant. X squared is a constant, so that's 0. X is a constant, that's 0. And y is a constant, that is 0, because we are differentiating with respect to y. So having seen that, we want to look at another simple, maybe a little bit more complex example, just slightly a little bit more involving in the computation, but the idea is the same. And here I'm putting up a problem that will force us to use the knowledge that we have for differential calculus, thinking about the issue of the product rule at the same time. So based on that problem, we want to solve the first part, that is the f of x, which we can write as df over dx. And therefore, I'm going to use the product rule to be able to work with this. And what does the product rule say? So I'll differentiate the first part, sine x, and keep the e constant. So this becomes cos x, e of xy, and then plus, I keep the sign constant, and now I differentiate e raised for xy. How do you differentiate the exponential? You take the power, and the power is xy. We differentiate with respect to x, so you get y e raised to power xy. So that is the first derivative of that f of xy with respect to x, partial derivative, partially, not the full derivation. So I can rewrite this equation. I can rewrite it as e of xy cos x plus y sine x. That is the first derivative of the partial, the first partial derivative with respect to x. Now, I can do the same, that is b, for f of xx, which is d squared f over dx squared. Because I'm more interested, I can use a product rule again, and then I separate. I assume this is one equation, and these are two equations. And that will technically be, if I differentiate this with respect to x, it becomes y, exy. And then I have this part remains the same because I'm using the product rule that we did in differentiation. So I've differentiated the first part because I've said I have two parts, part 1 and part 2. So now my first is I've differentiated e raised power xy with respect to x. So I got y, then plus everything. That is the first part of my solution. And then plus. Now I keep this constant. I differentiate what is inside the bracket. Now, if I differentiate this with respect to x, it will give me that, plus this, it will give me that. So that is a solution that I'll get from all those equations that I have there. You note that I can have some like terms, or I might not have any, to be able to combine them together. And I highly doubt, let me see, that is sine and cosine, and the sine and the cosine. Yeah. So yes, I'll not exactly have like terms per se, but you can put them together if you would like to do so. Now, what about for C, f of y, which is df, the partial, dy. Now you see that I'm only going to differentiate the exponential, so it will be x sine x e raised to power xy, because I've only differentiated this part. And when I differentiate the power of the exponential, I differentiate with respect to y, I get x, which I put down here. Then sine x is x, so I treat it as a constant, and that should give me the solution. So that one was slightly different. What about part D? If I get the second derivative, it will be, everything else will be constant. I'll only be differentiating the exponential, which will give me x squared sine x e raised to power xy. And that's what I'll get. And I could also get the derivative of f of y and then x. That is, I take equation C and now differentiate with respect to y. I'll get xy sine x e raised to power xy. Now, maybe most of you are asking, why is it the case? Remember, when you're differentiating the exponential, you differentiate the power and then you put it on the side. And that's what we normally do. Maybe I'll develop more videos on the normal for differentiation in calculus that we normally have. So I hope you've been able to follow. And again, if you like my videos, please do subscribe. It is nice so that you'll be able to continue to follow what we are doing together. Thank you.